Hello and welcome to Lecture 4 of Vectors, and just like we did with the last unit, we did a lot of drawing and we finally put numbers on it all. And so this is the lecture in the Vectors unit where we put numbers on all of it. So your friend Sam, who we've met before, isn't very good at giving directions, and you're trying to teach Sam to give better directions. So Sam is standing down here at the tail of this vector, and you're going to give Sam directions to get to the head and make them as clear as possible. Sam can't see the vector, but you're standing up on top of a nearby building, and you can see this vector just fine. So you say, okay, Sam, look over to your right. You see that great big orange x-axis. I want you to walk in the direction it's pointing, so parallel to it, for 4 meters. So Sam does that, and Sam winds up here. And you say, okay, Sam, now look over the other way. You see that big y-axis. I want you to walk in the direction it's pointing for 2 meters. So Sam does that, and lo and behold, here Sam is at the other end of the vector. And so we sort of just used these two vectors to build A, right? Sam wound up at the other end of A by following these two vectors. And one of them is parallel to the x-axis and the other is parallel to the y. So let's call them AX and AY. And they're kind of special. First of all, you could have told Sam to walk the other way, right? Along AY first and AX second, and Sam would have wound up in the same place. So the order doesn't matter. The other thing is we've seen diagrams like this. Look, when we have head-to-tail vectors that take you to the same place as another vector, that tells us there's an addition relation going on like this. It's useful to think of our vector A as being made out of AX and AY in some sense. And that's fine. Just remember, though, that you could make A out of any number of other pairs of vectors, in fact, an infinite number of possible pairs. But AX and AY are special. They're parallel to the axes, and that makes them very convenient. And so we give them special names. We call them component vectors. Here are several vectors, A, B, C, and I've broken each of them into its component vectors. And let's think about how we might write this component vector AX. Well, we could use magnitude direction form like we've been doing, and I could call it 4 meters, and I could say right, but I'm going to say in the positive x direction. And that's fine. There's another way I could do this, and it involves defining something new. I'm going to define a vector that points in the positive x direction, and I'm going to call it I, and I'm going to put a little hat on it, and that hat means that this is a unit vector. It has magnitude 1. And its partner here, J, is similar, but points in the positive y direction. And so these hats, whenever you see a hat on a symbol, that's telling you that that symbol is standing for a unit vector. So with that, I can define I that way and write AX because we know how to multiply. This is a vector. We know how to multiply a vector by a scalar. And I has a magnitude 1, so 4 meters times I must have a magnitude 4 meters. And note the meters are out here. That I hat is unitless. But now look what we've got. This is very useful because we now have a new way of writing A. Because we already know that A can be written as the sum of its two component vectors. But you now see that AX can be written 4 meters I. And AY can be written as 5 meters J. And I can do the same thing with these other vectors. So I can write B as 1 meter times I, and now be careful because this is negative, right? BY points in the negative y direction, so I'd better say negative 6 meters J. And C is negative 3 meters I plus 1 meter J. And so these things here, these factors that are before the unit vectors. This is the size of ax. So I'm going to call it ax with no vector symbol. And this is ay with no vector symbol. So these are scalars. They are the magnitudes of the component vectors. And I'm just going to stress again, this is part of why it's so important to draw your vector symbols when you're talking about vectors. Ax vector, axy, these component vectors are vectors, but these are scalars. And we call them components, not component vectors. The magnitudes of the component vectors are these things we call components. So this new form we have of writing vectors is called component form. Sometimes it's also called Cartesian form. And so this is a new form, different from magnitude direction form. And it's going to turn out that there are a lot of things that are much easier to do when you're working in component form than when you're working in magnitude direction form. In particular, it's way easier to add vectors in component form. So it's going to be useful to be able to go back and forth between component form and magnitude direction form. So let's do that. Let's convert A over to magnitude direction form. Now notice, the reason these component vectors are so convenient is that they're perpendicular. And so we've taken our vectors and we have turned them into something that we can think of as right-angled triangles. And we know how to deal with right-angled triangles. That's trigonometry. And I'm sure you've been looking forward to doing lots of trigonometry in this course. I sure have, so let's go. So if I want the magnitude of A, this is the magnitude of A. And if I just write A with no vector symbol, that's what I mean, the magnitude of A. Well, that's just the length of this side of the triangle. Well, you've learned Pythagoras' theorem ages ago, I'm sure. Okay, so 4 meters squared plus 5 meters squared, all square rooted, is about 6.4 meters. And now I can find the direction. So to find the direction, we need to define an angle. So I'm going to define this angle here as, I'll call it theta. And we just do our usual trig. Our opposite is AY over adjacent would be tan theta. And so theta is just the inverse tan of AY over AX. So that's 5 meters over 4 meters. And so that's the inverse tan of 1.25. Which is about 51 degrees. Okay? And I see students all the time just assume that with tan, the vertical one is going to go in the numerator, but be careful. Remember, this is opposite and adjacent that you have to think of. So up here, I'm going to come up here and I'm going to define for C this angle phi. Okay, and now you see tan of phi is going to be the opposite, which now is cx with that definition of phi over cy. And so you could find phi as the inverse tan, you can punch it into your calculator, of cx, which is 3 over cy, which is 1. Be careful, right? The component cx is really -3. I'm just trying to get an angle here, so I don't care about that negative. Now let's go the other way. Let's start with a vector that's in magnitude direction form, and let's get it in component form. So let's say there's a football here. Actually, the way I've drawn it, it looks more like a lemon. So let's go with that. Someone's throwing lemons. So here's a lemon that somebody's thrown, and it has a speed. Note I didn't put a vector symbol here, right? This is a speed. It's going 15 meters per second, and it's directed 30 degrees from the vertical. So we could write the v vector, the velocity, in either of these ways, say, and a variety of other ways. And let's convert that over to component form. So the first thing to do is just draw a little more. Before you do trigonometry, you should know what the triangle is that you're talking about. Never do trigonometry without drawing the triangle. So here is V, and here are its components, right? So these are V, Vx, Vy. And we want to know Vx and Vy. And we know that this is 30 degrees, and we know that this is 15 meters per second. So we can just do usual trigonometry. Vx over V, that is the opposite over the hypotenuse, and so that's sine of the angle we're talking about, so 30 degrees, right? And so Vx is V sine 30 degrees. Right? And similarly, you can see that Vy must be V times cosine of 30 degrees. More or less 13. Okay, and there. So to go from magnitude direction to component form, just draw the triangle and do the trig. Okay, the camera pans back to reveal that the lemon thrower was standing on the side of this hill with a 20-degree grade. And so now let's find the velocity vector again, but it might be convenient to work in axes that are referred to the hill. So just for sake of argument, I'm going to put my x-axis pointing downhill because I'm allowed to do such things. And let's go and find the vector in these coordinates. Because now, if you think through the geometry of this, here's a perpendicular to the hill. And the thing to notice is that this angle in here is 20 degrees. And that gray line there is parallel with the y-axis. And so our v, if we slide our v over to where the axes are and do that geometry, we see that this angle here is 50 degrees. And so now in our new coordinate system, we've got this situation. There's our v, here's our vx, here's our vy, and this is 50 degrees. And so we can do it all again, and I'm just going to take a slight pause to do that. Okay, so I've carried out the trig, and I've actually deliberately made an error, because look, vy is fine, but look at this vx, and compare that vector with these axes. Its x component is back in the negative x direction. So I'd better be careful here. I should now write this as negative 11.5 meters per second I plus 9.6 meters per second J, where now, under these axes, my I points this way and my J points this way. The real advantage of component form is that it makes vector addition really easy. Here's an A, here's a B. I've drawn the vector addition, and you just have to collect the i's and the j's. Or in other words, you add the x components up, so you're going to get negative 6 meters plus negative 2 meters, I plus, and that's 3 meters minus 5 meters, j, and so that's it. Negative 8 meters I minus 2 meters j.